Hi there. In today's lesson 3, we're talking about radian measure and how it's related to the unit circle. So let's get started. I'm going to use this top image here to talk about a central angle and an intercepted arc, and then we'll use the bottom one to talk about what a radian measurement is. So our central angle is any angle whose vertex is at the center of a circle. And the intercepted arc is the portion of the circle whose endpoints are sitting on the sides of that central angle. So the endpoint here and then the endpoint here. So this section would be our intercepted arc. So let's identify those on our image. And you can see we have done just that. So a radian is the measure of a central angle of a circle that intercepts an arc equal in length to the radius of the circle. So we can represent that this way on our picture. So when this radius from the center to the edge of the circle, that radius, and this radius, and this arc here, when they're all the same measurement, so if this radius was 1, and the arc was 1, and that radius was 1, that would be our central angle theta. Theta would represent 1 radian when the radius is equal to the arc. Okay, so when they're the same amount, that would be 1 radian. And if you think about it, if pi is 180 degrees, then this is pi radians, and 180 degrees, they're equivalent. So 1 radian would represent 180 divided by pi. And if you get your calculator out, if we called that our theta angle, which is our central angle here, then theta would be roughly 57.3 degrees, because I divided 180 by pi and got 57.3 degrees. So 1 radian is just about 57.3 degrees. So let's jump into our lesson here. If we want to find the measure of the angles below, the first one, find the radian measure of a 60-degree angle. I could set up a proportion and say 60 is to 180 degrees, as I don't know is to pi radians. So if we cross multiply, we have 60 times pi divided by 180, and that's going to give us pi divided by 3. So 60 degrees is equivalent to 1/3 of a pi radian measure. If we want to convert 85 degrees to a radian, we'll do the same proportion. 85 is to 180 as x is to pi. And cross multiplying, we're going to end up with 17 pi divided by 36 is our radian measure. So 85 degrees is equivalent to 17/36 of a pi radian. And then finally, part C, if I convert 2.5 radians to degrees, using that same approach, we have 2.5 is to pi as x degrees is to 180 degrees. And here I need my calculator. So 2.5 times 180 divided by pi is approximately 143.24 degrees. So x is about 143.24 degrees. So we're using conversion factors there. And at the top of this page, we're going to record what we just found. If I want to convert degrees to radians, then I multiply by pi over 180. So my conversion factor is pi over 180. And similarly, if we want to convert the other way, convert a radian to a degree, we're just going to use the reciprocal of that, and we would multiply 180 degrees divided by pi. So let's see how that works with example 2. It's using dimensional analysis. We're going to convert pi over 2 radians, because a radian doesn't have a unit mark like a degree does. So 180 has a degree divided by pi, and you can see the pi's cancel. So 180 degrees times divided by 2 is going to leave us with 90 degrees. So pi over 2 radians is equivalent to 90 degrees. And then going the other way, if I have a degree, I need to turn it to a radian, which is our pi measure, and get rid of the degrees. So our degrees cancel. 225 times pi divided by 180 would simplify to 5 pi over 4 radians. Part C, 2 radians. We're going to convert 2 radians to degrees. So 2 is my radian. I'm turning it to a degree, so I want degrees in the numerator, divided by pi. And we need a calculator for that. So 2 times 180, that's 360, divided by pi is roughly 114.59 degrees. And then part D, our last one, we're taking 150 degrees and we're turning that into a radian measurement. So pi divided by 180 gives me 5 pi over 6 radian measure. In example 3, we want to find the exact value of cosine of pi over 4. So cosine of pi over 4, we know pi over 4 is a 45-degree angle, and the angle, the side measurements for a 45, 45, 90 are 1, 1, and square root of 2. We also know cosine is the side adjacent our angle of interest divided by the hypotenuse. In this case, cosine of pi over 4 is adjacent over hypotenuse. And if you rationalize the denominator, we find that square root of 2 over 2. And then using a calculator to get the decimal approximation, that's going to be 0.707. So we know the exact value and the decimal approximation. In part B, sine of pi over 3 is the side opposite divided by the hypotenuse. And we know pi over 3 is the same as a 60-degree angle. And using those reference triangles from geometry with 60 degrees, the side opposite 60 degrees is radical 3. The side across from 30 degrees is 1, and the hypotenuse is 2. So the exact value for sine of pi over 3 is going to be square root of 3 divided by 2. And using our calculator for decimal approximation, that's going to be about 0.866. In example 4, we're looking at the length of an arc. So when I want to find the measure of that intercepted arc, when the circle has the radius r and the central angle is theta, theta has to be in radians. You might want to highlight that. It's a must that theta be in radians. So I'm going to highlight that. Theta has to be in radians. And the length of the arc can be found by using the formula S equals r theta, as long as theta is in radians. So let's give that a try. Let's use the circle at the right to find the length S to the nearest tenth. So if S equals r theta and our r is 3 inches and our theta is in radians, we're looking for this arc length from here around to here. So our theta is 5 pi over 6. Then we have 15 pi over 6, or 5 pi over 2 inches. And if you convert that with our calculator to the nearest tenth, we're going to find 7.85, so roughly 7.9 inches for the measure of that intercepted arc, 7.9 inches. Can go back and erase this. Okay, and then in part B, we want to find the length B to the nearest tenth. So the length of B goes from here to here. It still has the same radius of 3 inches because this radius, and this radius are all the same. And our theta is 2 pi over 3. So S equals the radius in inches times our theta, 2 pi over 3. So the 3 divides out, that's 2 pi radians, but to the nearest tenth, that's 6.28. So to the nearest tenth, the intercepted arc for B is 6 3/10 of an inch. So B is about 6.3 inches. And then example 5, we've got a picture. Let's go take a look at that. Use the graph to find the intercepted arcs here for angle AOB. So AOB, we want the length of this arc here for angle AOB. And it looks like the radius is 4 units and theta is pi over 4 radians. So to find the length of that arc, S is 4 units times pi over 4. So our exact answer is pi units, and if we use the calculator, that's about 3.14 units. So angle COD, so COD is over here, and our angle is pi over 3. So we can put that together. So the angle is the arc is 4, and the angle is pi over 3, which makes the intercepted arc 4 pi over 3. And using our calculator would be 4.19 units. Then part C is angle AOC, so that would be a 90-degree angle, which is pi over 2. Intercepted arc, radius is 4 times pi over 2, which gives us an exact measurement of 2 pi for the arc, which is about 6.28. And lastly, that's a typo on part D. It should be asking us to look at angle AOD. So we've got to add up the angle all the way over here. So if this is pi over 4, this is pi over 4. So we have pi over 2 up to the y-axis and another pi over 3. So if we add those together, pi over 3 plus pi over 2, we've got 6 in the denominator, and 5 pi over 6 for angle AOD is 5 pi over 6. So again, the arc is 4, and our angle is 5 pi over 6, and 2 divides 4, and 2 divides 6. So we have 10 pi over 3, and then using our calculator, that's about 10.47. So the arc from AOD, that entire length is about 10 and a half. And then our last example, a real-world connection, says we have a weather satellite is going in a circular orbit around the Earth. It completes one orbit every 2 hours. The radius of Earth is about 6,400 kilometers, and the satellite orbits 2,600 kilometers above Earth's surface. How far does the satellite travel in 1 hour? So we need our calculator again. And if you draw a little picture here, we know that we've got the Earth here, and 6,400 kilometers is the radius. So from the center of the Earth to the surface at 6,400. And the satellite is going to orbit another 2,600 around the Earth. I apologize for my circle drawing skills. So extra 2,600 from here above the Earth, 2,600. So putting those together, if we add them, the radius of the orbit is going to be 6,400 plus 2,600. That's 9,000 kilometers, 2,600. And what else do we know? We know the theta, so the central angle when we go all the way around the Earth, one complete revolution, then our theta is 2 pi radians. And we're going to use the formula S equals R theta as long as theta is in a radian measure. So in one complete orbit, we know in one orbit, the length is 9,000 kilometers times 2 pi. So let's use our calculator and find out that one orbit is roughly 56,548.66 kilometers. But the problem said that the satellite did that in a 2-hour time period. So we want to know what distance the satellite travels in 1 hour. So in 1 hour, we're going to divide by 2. The satellite travels about 28,000. Satellite travels 28,274 and a third kilometers in that 1 hour time period. And that's the end of lesson 3.